today we have the continuation of inverse kinematics, and you're going to look at 6 DOF manipulators. As we started in the last lecture, we saw that the inverse kinematics is strongly dependent on the structure of the robot. There is no single approach to solve the inverse kinematics of a manipulator. Every solution is dependent on the kinematics of that manipulator, with one exception. Whenever the robots have spherical joints, we can use that to simplify the problem. You remember from lecture 6, we are trying to work from the tip backwards towards the base, right, reducing the number of degrees of freedom as we go. And you can do the same with a 6 DOF robot arm, provided that it has a spherical joint. So not all robot arms will have an analytical closed form solution for its inverse kinematics. There are 2 conditions, and this is a good question for a midterm, that have to be met for a robot to have a closed form inverse kinematic solution. The first one is that 3 of its joints must be parallel. 3 revolute joints must be parallel. The second condition is that 3 of its joints must have a rotation axis that intersect in a common point, which is a spherical wrist joint. So if these 2 conditions are met, we can find a closed form solution to the robot arm. So the first condition is 3 revolute joints must be parallel. The second condition is 3 joints, the 3 final joints must have actuation axes that intersect in a common point. If those conditions are met, then you can find a closed form solution for the inverse kinematics. And that's why when you look at the design of most industrial robot arms, they always follow that specific configuration. You have 3 revolute joints, like the macadamic, and then you have a spherical joint connected to them with an additional 3 degrees of freedom. The motivation for that is that we can find a closed form solution for the inverse kinematics. So that explains why they all look alike. So today you're going to expand what you saw in the last lecture and try to use that to solve the inverse kinematics of a 6 DOF robot arm, such as the macadamic that you use in the labs. So just a quick review from the last lecture. We did the forward kinematics. That is easy because there is only a single solution to that. We give all the we give the DH parameters. We calculate all the transformation matrices. We input the variables we can control, and the output here is 2 vectors. Well, 1 vector and 1 matrix. 1 vector that gives the position of the end effector, and the other one that gives the orientation of the end effector. Combined, we create the homogeneous transformation, and in the homogeneous transformation we can get analytical expressions that give the position and orientation of the tool tip. The inverse kinematics is a bit more complicated because now we specify a desired position and orientation, and our job is to find the inverse procedure that now outputs all the actuation variables. In other words, given a desired position and orientation, where should we put each joint, each prismatic or revolute joint? If you consider the macadamic robot arm, this is what we tell the robot when we want it to go to a given position. We are telling it to go to a Cartesian position in a given orientation. So mathematically, what we say is we are specifying the desired homogeneous transformation from the tooltip to the base of the robot. And then you have to find the joint angles 1 to 6. So we have a total of, remember, they have a 4x4 matrix. The last line is constant. So we have the remaining 12 cells in the matrix that are equations that are now dependent on theta 1 to theta 6. So we have 12 equations, 3 positions, 6 orientations. For the 6 orientations, should be 9 orientations. Right, those are the components of the rotation matrix. Out of those, only 3 are independent. So you have 3 rotations, 3 positions. So I have 6 independent equations that I have to use to solve for 6 variables. So that is not a very trivial task. We solved this one in the last lecture. We're going to use this one again. That's why it's here. Right, this is a 3-arm robot arm. And how did we do this? We specify the position of the tooltip by saying that we want the robot to go to position px, py at an angle phi. Given that and given the length of the robot, we could move back to this point here by using a simple trigonometric relation. And now instead of dealing with the tip of the robot, we are dealing with the end of joint frame 2. With frame 2, or the end of link 2. If you do the forward kinematics using the DH parameters, we have that giant matrix. So where is the Cartesian position here? So those are these 3 points. First one is px, second one is py at the tooltip. And you can see that they are functions of the preceding joints. So here we have now, all we have to do is to take these 2 equations and somehow solve for theta 1, 2, and 3. So here's our 2 equations. Here's the third one that I get from the specification of the orientation angle phi. Okay, so what was the approach again? To start from the tip and see if we can simplify the degrees of freedom by moving back using simple trigonometric equations and then solving for the remaining variables. Right? So that's the way we did that. We found theta 1 and theta 2 using some mathematical manipulations. Those are the equations we came up with in the last lecture, and that's the relation is how we find the last angle based on the desired orientation in the other 2. Okay, so that's what we did in lecture 6 for a 3-DOF arm. Now let's see if we can use the same approach in a 6-DOF robot arm using now a combination, not a combination, but not a plane, an arm that is on a plane, an arm that can move in 3 dimensions. So this is what we're going to consider, a 6-DOF robot arm having a spherical wrist. And a spherical wrist is simply a combination of 3 joints, and the actuation axis of those 3 joints will intersect at a common point. So here we have the last 3 joints. If we draw the actuation axis for each of them, this is one, that's another one, and that's a third one. The point here where they intersect, you're going to call that the wrist of the robot arm. Right, so I have 3 consecutive joints that intersect at a given point. That's a spherical joint. And that position there is the wrist position. You can see here in these 2 examples, we have a spherical joint at the tip. That one is around here. The macadamic has one as well. If you look at the 3 end joints, they will intersect at a common point. So you have that last joint that rotates, and you have one like this, right? The spherical, the wrist is just behind that axis, and is the point where these 3 consecutive axes intersect. Now, one assumption they're going to make here to simplify our problem is that the position of the wrist only depends on the first 3 joints, and the orientation of the wrist only depends on the last 3 joints. Is that clear? The position of the wrist depends on the first 3. Its orientation depends on the last 3. Right? For my shoulder here could be a spherical joint. Right? My torso is what determines its position. And then the other 3 axes here is what determines the orientation. I'm not talking about the end effector. I'm talking about the position of the wrist. Does that make sense so far? Yeah? Okay, so our problem is, given a desired homogeneous transformation from the tooltip to the base, in other words, give a desired Cartesian position for the tooltip and a orientation of the tool or the end effector, find theta 1 to theta 6, that will now give us that homogeneous transformation, which is a function of theta 1 to theta 6. First assumption I'm going to use is what we just said. The wrist position depends on the first three joints. Second is the wrist orientation depends on the last three joints. So if we want to find that point, if you could find that point, we can now split the problem into two. Find the homogeneous transformation that will now position the wrist here, and find the orientation of the wrist axis that will now point down. So we are splitting the problem into two, into a Cartesian requirement of placing the wrist there, and then using the rotation matrix we could find the orientation of the wrist. So in other words, this is what we are looking for now. The position of the wrist and its orientation. What is the orientation of the wrist? Well, it is given by the homogeneous transformation that connects the tip of the robot to the wrist point. That is homogeneous transformation 6, the tip, to joint 3, which is where they intersect. Does that make sense? So you're now splitting the problem into two. Find the wrist, the Cartesian position of the wrist, and find the rotation that now links the desired end effector and the wrist to put that in the orientation we want. All right? Again, our input is always t from 6 to 0, the desired position and orientation of the tooltip. Yeah.
What was the second rotation?
The second rotation?
So we need to find the Cartesian position of the wrist.
Yes, that's W. And then this is the rotation matrix from the tooltip to the base of the wrist, or the position of the wrist. Yeah.
Explain the 3 to 6 again.
Yes.
For the rotation of the wrist.
Yeah. So forget about the rest of the robot here. Right? So if you're only dealing with this position and you have the arm pointing like that, how do we find the orientation? Well, we would need to find the homogeneous transformation that connects the tooltip to the base. Our base is that in this point, right? So this we can extract from the homogeneous transformation that connects this point to that point. So it would be, if that was our base, it would be 3 to 0. But it turns out that at this point is not 0. This point is the third link. So instead of going, because it's attached to other links here. So instead of going from 3 to 0, we go from 6 to 3. That's the homogeneous transformation that now specifies position and orientation of the wrist. From that, we take the first 9 elements, which are the rotation matrix. Sorry, that's what I wasn't showing there. Okay, so here we go. First things first, let's try to find that point. What do we know? What we know is T0, 6 to 0. Why do we know that? How do we know that? That's the desired position and orientation. So look at that as a numerical matrix. There's no variables in there. There is just numbers specifying the Cartesian position and and the orientation of the wrist. So that is known. Right? If we know that, we also know the orientation of all axes of frame 6 that is connected at the tooltip. Because we know the entire rotation matrix. We know exactly how the 3 axes of the tooltip are oriented in space. Correct? Does that make sense? Because you're telling the robot, go like that. Right? Go with a tip like this and that. And that, blah, blah. That's specified in the rotation matrix. So we know that, and we know the position of the frame at the tip of the robot. Our last actuation axis there is Z6, and it points down because it is going along the last actuation axis. So if we know this point over here, one second, if we know this point here, what is the relation between the blue and the red point? The red point is the blue point shifted in the negative z axis by d6. Shifted in the negative z axis by d6. Does that make sense? Right? So we can look at that as along a line of the vector vector z6, which is the coordinate of the last axis. Or we can simply find the projection of d6 in each axis of the sixth frame and then shift it backwards. And that's pretty much what it is saying. So here is the equation. The wrist position, which is a 3D Cartesian position that we see here, is P, the point at the tip of the robot that also has 3 Cartesian positions, x, y, and z, shifted back by d along z6. Does that equation make sense so far? Yeah? Okay, so that is the vector form. If you want to expand that into 3 equations, we can also get this. This is the wrist position. It has coordinates in x, y, and z, right, which are related with the respective components of px, py, and pz. Now notice here, we take px minus d6 times r13. What is r13 from the rotation matrix? Is the coordinate of z6, the projection of z6 onto x, 0. What is this one? Is the projection of z onto y, 0. Projection of z onto z, 0. Right? So these 2 equations are the same. They're just, this is of the vector form, and this is the expanded version for each element. Yeah.
So what's the flashing? So the blue point is always like perpendicular to the red one?
No, the blue point could be anywhere in the space. There is no constraints here.
Because you just told is the around the z.
Z happens to be pointing down now, but Z could be pointing in any direction.
Oh yes, if you allow the exercise, so the distance always be d6, but it could be have like this the different position. You can have different projection.
Exactly. So if Z6, in this case here, projections on X, Y would be 0. Right? Projection of Z would be negative d6. If you know the robot points at an angle like that, then these will change. We know this from T, right? Because we are specifying the orientation, the desired orientation. Does that make sense? Yeah? Okay, so all these components are known. We can now shift our problem from Z6, from P back to the position of the wrist. And now we can split the problem into 2. Once we find the position of the wrist, we can try to solve for theta 1, 2, and 3. That will give the position of the wrist. And then later solve for theta 4, 5, and 6. That will give the orientation of the wrist. So, if this is theta 1, theta 2, theta 3, we can tell that the position of the wrist does not depend on theta 4, 5, or 6. Right? So our job is to find the position of the wrist W using theta 1, 2, and 3, and then find the orientation of the wrist that only depends on 4, 5, and 6 through the transformation, the rotation matrix that connects the end effector back to the wrist. And how do we do that? Easy. Easy, easy. Because once we determine the position of the wrist in space, we'll have theta 1, 2, and 3. If we have theta 1, 2, and 3, we will know the rotation matrix from the wrist to the base. Correct? We'll have W. And if you have W, then we know the orientation of the wrist back to its base. So we know W, we know R3 to 0. Yeah? What else do we know? We know the desired orientation of the tooltip with respect to the base. That's the input. That's what you want to solve for. We are looking for, we know this one as well because, we know this one as well because you now solved for theta 1, 2, and 3. What goes here is 6 to 3. We know, does that equation make sense? We know that the rotation from 6 to 0 is the same as the rotation from 6 to 3 times the rotation from 3 to 0. Well, that's that cascade operation that we've been using to find the forward kinematics. Does that equation make sense? Yeah? So what do we know here? We know this because it's the input. We know this once we solve for theta 1, 2, and 3. And we are looking for that. That is only a function of theta 4, 5, and 6. Because it's only the orientation of the wrist. Does that make sense? So this is the equation we will start from. How do we solve for theta for R6, 3? Well, just do some manipulation. Move this guy to this side here with the inverse. All right, so that's that. And remember that this is a rotation matrix. In a property of the rotation matrix is that its inverse is the same as its transpose. All right, so we can, instead of inverting, we just write the transpose, which is a lot easier to calculate. So let's summarize the procedure one more time. We are specifying T6 to 0, and by consequence, R6 to 0. We are finding, now we know how to go from the position of the end effector back to the position of the wrist. We can then solve for the position of the wrist. We'll do that later. And that will give us theta 1, 2, and 3. Once we have theta 1, 2, and 3, we will know T3 to 0, and also from it R3 to 0. What is missing? We'll know where the wrist is. The only thing we need to know now is the orientation of the wrist. How do we connect everything? Through that, we know that the rotation from the end effector to the base is the rotation of the end effector to the wrist times the rotation of the wrist to the base. This is what we're looking for now to solve for the last part. So you have now two jobs. Find theta 1, 2, and 3 to give the position of the wrist. Then find theta 4, 5, and 6 to give the orientation of the wrist through that. Does that make sense? Any questions? No? All right, so let's do that. We know how to go to W from the end effector. Yeah, that's clear? Yeah? Sort of? Using the projections, we go from the tip back to the wrist point W. So we can forget about the other three joints for now. And then just consider this, so the first three of them. The input here to this problem, what we know is Wx, Wy, Wz. I can now place that in space and then calculate the projection on the base frame here. This is the projection on Y. This is the projection on X. What is the height? The height is the z component of the wrist position. From that, we can calculate theta 1, because if you look at the position down here, the projection down here, this point is directly affected by theta 1. So how do we find theta 1? Trigonometrically. What do we know again? We know w, x, y, and z. So we know this projection, we know that projection. What is theta 1? Is the inverse tangent of
X, y of x, or y over x.
exactly wy over wx. This and that. Does that make sense? Very good. What would you guys do next? Now we need to look for theta. We already solved for theta 1. What do we do next? Well, we find theta 2 and theta 3. Think about what we just did in the last lecture, and I just summarized here. Do you see anything similar?
You can constrain theta 2 and theta 3 based on theta 1.
We solved for theta 1, yeah? So we don't need to know anything else, can go to this point here. Now this is now reduces to a two-arm parallel system, which is exactly the one we just solved, isn't it? But it is operating on this plane here. It shows better on your copy there, but you see that there is a plane here like that. Now that this two-arm is operating on that plane. What is the desired position? Remember that before we solved for the system by specifying the position x and y of the tip. What is x and y for this one? On this plane where it operates, like that. On that diagram, what is the desired position of the tip, of the wrist? Would be R, yeah, R and S. Right? Because now this becomes a 2D problem. If we forget about that, right? Well, the robot is in that orientation that is given by theta 1, so this plane here rotates at theta 1. And in this plane, there is a two-arm mechanism operating. The desired position of the tooltip now, which is W, is R and S within that plane. Does that make sense? So, if you determine R and S, then you can use the exact same equations we solved in the last lecture to find theta 1 and theta 2 and theta 3. Yeah? What is R? Aha. R is this distance over here. We know this distance and that, so R is the square root of wx squared plus wy squared. Alright, so here is the another view. So this is taken from this point, from this plane. Alright, so the position of the tip is R and S. What is S? What is S? How do you calculate S?
EZ.
Aha. WZ,
WZ, sorry.
which is this.
It's adjacent
WZ minus D1. D1 is fixed, right? Is this height here, is a characteristic of the robot itself. Now what do we do with this? Now we are specifying the desired position of this two-link arm in that plane that rotates about Z, like this. Now that translates about by theta 1. Is this clear? Right? We know everything here, right? We know all these. Now, when you know all that, it comes from the operation we did before. We can now find theta 1 and theta 2 using the very same equations we had before. The only difference is that now here, instead of x and y, we have these s's. So you have this extra manipulation to do. Does that make sense? Yeah? Okay. Are you sure?
It's a lot.
It's a lot to take in. Yeah. Okay. I'm not so sure that this is clear because I've probably taught over 400 lectures in the last 4 or 5 years. I can tell when students are following or that they don't, when they pretend. Okay, can we move on? Okay, what is our next job now? We found the Cartesian position of the wrist. The last part is to find its orientation. Now notice here that the position of the wrist indeed only depends on theta 1, 2, and 3. The orientation of the wrist, on the other hand, only depends on theta 4, 5, and 6. So now our job is to solve for this rotation matrix given the other two. We now have both of them. The left most, what is this? Right. The most right one is from the desired position and orientation. This one, the transpose, is the one we get from the forward kinematics connecting the base and the wrist. So just the forward kinematics, these are the DH parameters of the first three links. They are functions of theta 1, 2, and 3. We find the homogeneous transformation from 3 to 0. Where is the rotation matrix? Is that. All right, so what we wanted to do is to solve for these guys here, but by solving this, we actually specified the rotation matrix from 3 to 0 that we need over there. Okay?
But then we also need to multiply by the rotation matrix from 6 to 0.
Yes, but we know that one.
Yeah.
We know that one because that's the desired orientation. It's just telling us how the end effector should be oriented. Now let's try to solve for that R 6 to 3. How do we find R 6 to 3 first? R 6 to 3 is a function of theta 1 to theta 4, 5, and 6, whereas the rest is just numerical values, known values. Right? So our only variable is that entire transformation matrix. We have a spherical wrist. So we can now take the DH parameters of the spherical wrist. That L1 here should change. This is actually D6. So those are the DH parameters of the spherical wrist. We can multiply the 3 homogeneous transformations, and then we have the homogeneous transformation from 6 to 3. Right? Does that make sense? From this homogeneous transformation, there are functions of the unknown values, theta 4, 5, and 6. We take the transformation matrix 6 to 3, the rotation matrix, excuse me, that's there. Yeah.
Should that T be 6 to 3, not 3 to 6?
Which T?
In the same way?
Sorry, which one?
In the text.
Up there?
Yeah.
No, that's right.
Okay.
That's right. Yeah. Oh, yes, it's flipped. It's 6 down, 3 up. Yeah. Okay. So you see that now this equation has 9 equations this matrix has 9 equations, all functions of theta 4, 5, and 6. How do we solve for it? Easy. There you go. Let's recap what we did here one more time. This is the rotation matrix from the wrist to the end effector that we calculated using the DH parameters of a wrist joint. This is the transposed of the rotation matrix from 3 to 0 that we know because we solved already for theta 1, 2, and 3. This is known because these R1s come from where? From the original specification of desired orientation of the tooltip. So all we have to do is to solve, expand these fine expressions. Now we have a lot more variables expressions to solve for, but remember that only 3 of these are independent. So you can find these independent equations and then try to solve for that. So let's transpose this matrix. What goes in the first line there if you transpose it? These two will shift. So you have sine 1 cosine 2, 3. These also shift. So you have sine 2, 3 minus cosine sine 2, 3 cosine 2, 3 minus cosine 1 and sine 1. We are almost done. We are halfway there. Now we are almost done. Just a simple, but you see where I'm going with this, right? Because now I can create expressions if I just multiply this out. Let's say, what is this equal to? This term here in the matrix. This term in the matrix with 3 unknown is equal to this times that. Everything is known. What is this term? This term is this times that, and so on. So I can create now several expressions and then eventually solve for theta 4, 5, and 6. So let's do that. This is only getting worse. Let's do it. What is this term over here? That term is this times that. So cosine 4 times sine of 5 is C1 cosine of 2, 3 times R1, 3 plus sine 1 cosine 2, 3 times R2, 3 plus sine 2, 3 times R3, 3. All right, so this times that times plus this times that plus that times that. So everything I have written in red, those are numerical values. We know them. All right, so now we have an expression that says cosine of 4 sine of 5 equals to whatever, right, a numerical value. And you can do that for all elements here and keep going. But we don't need all of them because remember that these 9 expressions are not independent. But interestingly, we have one here where you can get cosine of 5 directly. What is the expression there? Is the last row multiplied by the last column? No. The entire row, x S1 multiplied by the last column, which is given here. Now, good news, we have theta 5. We have theta 5. If you just do arc cosine of theta 5, solve for that, we got theta 5. Of course, we wouldn't do it that way because it's too simple, right? So we need to somehow complicate it even more. So how can you possibly complicate it even more? By using the A tan2 function. Right? So we can keep track of the quadrants. So we could do that, but remember that the cosine doesn't keep track of quadrants. So if you have the cosine, we can calculate the sine of 5, which is the square root of 1 minus cosine of 5. Sine squared, excuse me. Sine squared plus cosine squared equals to 1. Right? So now they have sine and cosine. We can define the tangent of 5 as that. the sine is taken from this when you replace cosine in there. Cosine is already given here. Now we can use the a tan 2 function to keep the track of the quadrants.
Will we get a question like this on the midterm?
Oh, for sure. Yeah.
So how do you get the S5? 1 minus 2 squared.
So we have sine of 5 squared plus cosine of 5 squared equals to 1. All right, so cosine sine of 5 squared equals to 1 minus cosine 5 squared, square root of both sides. I'm not going to ask you inverse kinematic equation.
It's tangent.
No, this one from here, right? Now the tangent is sine over cosine.
Okay.
Yeah. So I'm artificially fabricating the sine so we can use the a tan 2 function to keep track of the quadrants. Well, let's keep going. How can we make this? How can we find theta 4 now using the tan function? Easy. Let's divide the sine. Let's divide this too. So if we divide, how do we do this? We divide this by that. We have cosine, we have sine 4 sine 5 divided by cosine 4 sine 5. These two cancel out. We have sine 4 divided by cosine 4, which is tangent of 4. We have expressions for both sine and cosine now. We don't need to create that artificially. So if we just divide this by that, is the tangent of 4. Does that make sense? Now notice once again that in all these expressions, everything in them is known. We already calculated everything. And that's the beautiful expression for theta 4. There are other ways, of course, to calculate it. And what is theta 6? We'll do the same, but now we divide these two. When you divide these two, we have S5 canceling out. We are left with this negative 1 here. So this is the tangent of a negative theta 6. Invert that, theta 6 is there. And then we have it. We have now theta 1, theta 2, 3, 4, 5, and 6. Isn't that nice? No, it is. It's an interesting problem. It's a very clever way, I think, to split that into two ways. So we could only do that. We could only do that again because we met two criteria. The first three links were parallel in series. The last three were spherical. They met their actuation axis passed through a single point. All right, so here's the summary of all we did. Theta 1, 2, 3, 4, 5, and 6 with the intermediate step here to calculate the R and S. There's one thing missing, which is to determine Wx and Wy. Remember from that expression we saw where we project the n effector along Z6, right? So that one is required to do that. And that's it. So there's a little problem with all this, is that for the macadamic, for example, for a given Cartesian position, there are 8 possible solutions. How do we know which solution to pick? How do we know if the robot can do it? We have to check them one by one. In the inverse kinematics already implemented in the macadamic robot, it will check which solution to go to. So instead, let's say you want it to move simply like this. Right? It will pick the solution that has the least amount of displacement. Otherwise, it could simply do that, just to move by a few millimeters. It wouldn't make sense. Right? If it can just do this, it will. But you have to check that one by one. So there you can see an example. Two same orientations, same end effector position, and yet different joint angles for certain joints.
So here the P point is the point of the list, right?
P point is the position of the end effector. One second. P goes here. W is there.
Then the S equals to PZ or the W then?
PS.
The third row, S equals to PZ,
Yes.
or it is W?
This is W. Yes, this is W. There's a typo here. All right, that's what we did over here. It was W indeed. A good catch.
No, that was WZ.
Yes, WZ.
WZ.
Yeah.
Exactly. Yeah.
Okay. Yeah. Okay. All good? Now, let's do an exercise here, see if we can make sense of all this. So here I have a different robot. I replaced two of the joints with prismatic joints. And the left the rest, just moved stuff around. Do we have a spherical joint? First question, do we have a spherical joint? And where is it?
4, 5, and 6.
Are 4, 5, and 6, do they make up a prismatic, spherical joint? So I'll do the actuation axis for the first one. Here, theta 4. Theta 5, up and down. So far so good, they intersect. What about the last one? Is also like that. It can rotate like this. Right? Coming out of the page, it rotates around that. Right? So the axis can travel like this, this sixth axis. And if it does that, it still passes through the same point. So there is indeed a spherical joint. And the wrist position is right here. Does that make more sense? So the only thing we need to determine is, are the axes of theta 4, 5, and 6 intersecting at a common point? It's clear that a 4 and 5 do. Right? And 6, just in this particular case, is oriented along theta 4. But if you rotate it like that, along 5, it still passes through the same point. So it is indeed a spherical joint. So how do we find the inverse kinematics? Break it up into two. What is the difference compared to what we just did? The wrist part is identical, doesn't change, so we can use the exact same equations for 4, 5, and 6. We can use the exact same equation to go from P to W. P is over here. P is over here. How do we relate them again? W is P minus D6Z6. So what is the only thing we have to do? Figure out the first three axes, theta 1, 2, and 3, that will give W. And then the rest is the same equations we just did. We don't have to recalculate that. So let's do it. What do we know? We know this point. Call that a W, which is WX, WY, WZ. We need to find all the variables that will bring us there. In this case, they are theta 1, D2, and D3.
Going back to the last one, why is it Z6 though? This isn't. In the other one, we were working with the negative side.
Yeah. Well, we happened, yes, but remember that a z-axis is always oriented along the actuation axis. So z6 is here.
Okay, that's just because of the axis right here.
Yes, but it's not pointing down. It's pointing along the actuation axis of the last joint, right? Which in the previous case happened to be down. All right, so this is what we know. How do we find theta 1, 2, and 3? Theta 1, let's put it over here. The projection down here is wy, wx. What is theta 1? What's theta 1? Is the inverse tangent of wy over wx. Done. First variable, done. What is d3? What is d3? Square root of wx squared plus wy squared. Right? We know all these, so that d3 can now be calculated as a function of that. The only one left is d2. We can find d2 by realizing that this is wz. What is wz? Is d1 plus d2. d1 is fixed, d2 is the actuation. So d2 is wz minus d1. So here they are. Everything else is identical to the previous example.